All right, so we're going to do section 6.2 now. In this section, we're going to describe the effect of performing a linear transformation on a random variable, combine random variables, and calculate the resulting mean and standard deviation, and calculate and interpret probabilities involving combinations of normal random variables. Yay! Okay, so let's just do a quick review. What are some things that we could use for the measure of a center, the measure of a spread, or the shape? So think about all those things of how we would normally describe them. So measures of a center could be mean, median, mode. Measures of the spread, you could do the range, the IQR, the standard deviation. And different shape things, you could describe it as skewed right, skewed left, symmetrical. I guess uniform is a type of symmetry. Usually we'll just say right, skewed, left, and symmetrical, or normal. If it is skewed, what would you choose for the measure of the center? So you guys said the median. What about for the measure of the spread? The IQR. All right. So back in chapter 2, we studied different effects of linear transformations on the shape, center, and the spread of the distribution. So think back to chapter 2, and this is a little summary of what we discovered. So adding or subtracting a constant to each observation changes the measure of the center, but not the shape or the spread. If I multiply each observation by a constant, it's going to change the center, change the spread, but will not change the shape. So if you want to put this in your notes, this is really good. Have it starred. Lots and lots of questions on the AP exam about that. So how does multiplying or dividing by a constant affect a random variable? So let's look and see. All right, so if I am multiplying, and remember you could multiply by a fraction, which is just dividing. So if I multiply each value of the random variable by a number b, then it's going to take that center and it's going to multiply it by that amount. Okay. With the spread, it's also going to multiply by that same amount, but it will not change the shape. So how did it perform? Hopefully you said just like we had seen back in chapter 2. Okay. Then I have a little note. Multiplying a random variable by a constant b multiplies the variance by b squared. Because remember, variance is standard deviation squared. Okay, what about adding or subtracting? Guess what happens? It's the same thing that we already learned. Okay? So let's look at this example. Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Define X as the number of passengers on a randomly selected day. Okay. So here's our probability distribution, and we can make a nice little graph of that, of what it would look like. So the mean of X, if we wanted to go find that, so the expected value, 3.75, and the standard deviation, 1.09. See if you can do that on your own. And again, I like to put them in the lists and do one variable stats, L1, L2. All right, so now it's going to say, hey, Pete's now going to charge $150 per passenger. The random variable C is going to describe the amount Pete collects on a randomly selected day. So if he had 2 passengers, so 2 times 150 would give you 300. If he had 3 passengers, he would make 450, etc., etc., etc. So still with those same probabilities. Here's what that distribution would look like. What does it look? Wow, that shape is exactly the same. The shape doesn't change when I'm multiplying everything. So here, if I wanted to find the mean, it would be 562.5. So what would you find the mean to be if you took 3.75 times 150. Did everybody get it? And I just put that in my calculator just to double check. I got 562.5. Oh my gosh! Okay, so I could just take this times 150 to get to the answer. So when I multiply the mean. So what about the standard deviation? Well, I also, when I multiply, changed the standard deviation by multiplying it. So sure enough, this guy times 150 is going to give you 163.5. Pretty cool. And the shape doesn't change when you multiply. That's what we just were discussing. I think it's cool at least. All right, so let's look at this next one. A large auto dealership keeps track of sales made during each hour of the day. Let X be the number of cars sold during the first hour of business on a randomly selected Friday. Based on the previous records, the probability distribution of X is as follows. Cars sold 0, 1, 2, and 3, and the probability of that. The random variable X has a mean of 1.1 and a standard deviation of 0.943. Check this and make sure you get the same thing. All right, so number 1 now says, suppose the dealership manager receives a $500 bonus from the company for each car sold. Let Y equal the bonus received from car sales during the first hour on a randomly selected Friday. Find the mean and the standard deviation of Y. So if you're getting that for each car sold, basically I'm going to multiply however many cars sold times 500. So if I am multiplying, then I multiply whatever that mean was by 500 to get my new mean. So his average that he's going to receive is going to be $550. And what about the standard deviation? Does it change when you multiply? It does. So I'm going to multiply it as well by 500. And the standard deviation is about 471.50. So 68% of the time he's going to be within 550 minus 471.5 and 550 plus 471.5. So there could be days where he's only making, what, 28.50? Or no, more than that, plus 50. So 58.50? 78.50. Okay, sorry. Okay. So, to encourage customers to buy cars on Friday mornings, the manager spends $75 to provide coffee and donuts. The manager's net profit T on randomly selected Friday is the bonus earned, then minus the 75. So here I'm going to take the bonus, so I have my 1.1, and I'm going to multiply by that 150, but I have to subtract the 75. So I can see now my new mean is going to be $475 if he likes to buy donuts for everybody. The standard deviation, I'm going to take my 0.943 times my 500. Do I subtract? No. When you add or subtract, that does not affect the standard deviation. So my standard deviation is still 471.50. All right. So, a report of the National Center for Health Statistics says that the height of a 20-year-old man chosen at random with a variable h with mean of 5.8 feet and standard deviation of 0.24 feet. Find the mean and the standard deviation of the height j of a randomly selected 20-year-old man in inches. And there are 20 inches in 1 foot. So for every 1 foot, I'm going to multiply by 12 to get 2 inches. So if I am multiplying, think about what changes and what doesn't change. So the things that change are the mean and the standard deviation, but not the shape. So to find my new mean, I'm going to take 5.8 times 12, and I would have 69.6. To find my new standard deviation, I'm going to take my old standard deviation times 12 and get 2.88. All right. Consider Pete's Jeep's chores again. We define C as the amount of money Pete collects on a randomly selected day. So here we saw that if I was to multiply everything through, I could see what that would look like. Okay. However, now we're going to throw a twist into it. Pete, it costs him $100 to buy the permits, the gas, the ferry passes, all that stuff. So now the random variable V describes the profit Pete makes on a randomly selected day. All right, so I'm going to take whatever I made and subtract 100 each time to get to these new amounts. So if I am subtracting, what changes and what doesn't? All right, so I do subtract with the mean. I do not subtract with the standard deviation. So the center is going to be smaller by 100. The spread will stay the same, and the shape will stay the same. And there's what the shape would look like. So in general, this is really, really good. The mean, you are going to add and multiply by b. The standard deviation, you multiply by b, which, well, the absolute value of b, because you can only have it be positive. So this is good to kind of remember when you're doing all your linear transformations. Now we're going to take two different transformations. We're going to combine the random variables together. So we're going to take two different events and combine them together. So if I have two random variables, x and y, and I combine them together by adding and call that guy t, then I can just add the expected values together. So in general, you can just say, well, the new mean is the mean of one plus the mean of the other. Okay, great. So let's see. If this guy has a mean of 375 and this one has a mean of 310, what is going to be the new mean? So how much could they expect? How many people are they going to expect now? So that expected value is your mean on any selected day for both Pete and Aaron. So you can just add them together and get 6.85. Now, to find the, let me keep going here for a second, and then I will pause. Okay. So in order to find the spread there, in order to talk about the standard deviation, we're going to have the events be independent events. Okay? So if they're not independent, then we're not going to be able to find the spread. I'm going to skip past that. And here you can kind of think about what's going on if we were to find all of these guys. But if you wanted to look at that, sweet, go back. So let's just talk about it. When I combine two independent, so these have to be independent, two independent events, so those two random variables, they have to be independent, I can only put the sum of the variances together. So if I want to find this new standard deviation, I am going to square root the sum of the variances. Okay? So you can never just add or subtract the standard deviations, and you are always adding when it comes to variances. Okay? Like even if it said x minus y, this one's always a plus. When you have the means, it could be a plus or a minus. But for adding the standard deviations. or the variances, and then square rooting to get the standard deviation. So back to this other guy. If I know this is the standard deviation for, what was it, Pete, and this one was for Aaron, then what's this new standard deviation? Well, the first thing I'm going to have to do is get the variance for each of those, add the variances together, and then take the square root. And that's approximately 1.44. And here we are assuming independence. Okay, so it told us to assume that those guys are independent. That was weird. Whoops. Okay. All right, so let B be the amount spent on books in the fall semester for a randomly selected full-time student at El Dorado Community College. Suppose that U sub B is 153 and sigma sub B is 32. Let C be the overall cost for tuition and fees for a randomly selected full-time student, and that mu sub C is 882.50, and the standard deviation sub C is 103. Find the mean and the standard deviation of the cost of tuition, books, that's supposed to say fees, and books, C plus B, for a randomly selected full-time student at El Dorado Community College. All right. So the standard deviation and the mean. So in order to find the new mean, if I'm going to add this all together, I'm going to take mu sub B plus mu sub C, which was 153, plus 882.5, and hopefully you get 985.50. Okay, what about the standard deviation? It never told us that they are independent. So are these tuition fees and cost of books independent? No, because if you're going to take more classes and have more tuition, then you're going to have more books. So they're dependent on each other. So since they're not independent, we cannot find the standard deviation. All right. See if you can do this one. And these are independent. Or sorry. Gosh, are they independent? Sorry, let's think about that for a second. We can't assume. So college uses SAT scores. I think people could argue, but I'm going to say that these are not independent events. That usually, if you do good on math, you're going to do overall good. Same for critical reading. Although that wasn't the case with me. I scored way better on my math than critical reading. However, in general, for most people, I think that they're going to be dependent, not independent. But the mean you can find, even though they're not independent, just add them up. And the standard deviation would not be independent. If they were independent events, just if, so if everybody was like me, then I would take 115 squared plus 111 squared and then square root to find your new standard deviation of of sigma sub x plus y. So your new mean of x plus y would be your 515 plus 507. Okay? And you could calculate what those would be. All right, try this one. Let me move that for a second for you. And you can pause me. And I'm going to go ahead and move on now. And let's see how you did. So to find the mean and the standard deviation of x and y, that's what I got. Then to find the new mean of the total here, you add up both of those independently, and I got 1.8. To find the standard deviation, and these were independent, it said assuming that they are independent in the problem, then you take each of the standard deviations, square, and then square root. I think I wanted you to interpret find and interpret? Yeah. So the expected value for the total cars is 1.8. So that tells us that, most cars are going to be around 1.8. And then the 1.14 tells us that the 68% of the time you're going to be within 1.14 of 1.8. All right, so then that new part says the dealership's manager gets that $500 bonus and a $300 bonus for the lease. Find the mean and standard deviation of that. So we can take 500 times the bonus for sold plus 300 times the bonus for the leased. And here I can see that that's going to give me a total of 1.14. Now the standard deviation, I'm going to have to take the standard deviation times the 500, then square to get to the variance. Take your standard deviation times 300, then square to get to the variance, and then square root that whole thing to get to your new standard deviation. Yay! All right, you guys are doing great. Now, subtracting. If I subtracted two things, the means are subtracted. However, the standard deviations are always adding. Okay, so you're always going to add with the standard deviation. You're going to add the variances and then take the square root. Always. However, the means are minus of minus, plus of plus. Put that in your notes. All right. So see if you can do this one. I'm sure you're going to do great. Pause, and then I'm going to go ahead and see how you did. And if you have any questions, let me know. All right, combining normal random variables. So far we have concentrated on finding rules for means and variances of random variables. If a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. An important fact about normal random variables is that any sum or difference of independent normal random variables is also normally distributed. All right, so here's an example. Mr. Starnes, he likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly, let's pause. In a randomly selected packet follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability that his tea is just right? So here we can see, let's let X be the amount of sugar in a randomly selected packet. Then I'm going to have the amount of sugar in packet 1 plus packet 2 plus packet 3 plus packet 4. And that will give me the total. So we want to find that total, what's the probability that it's going to be between 8.5 and 9 grams of sugar. Okay. So, well, let's see what our mean would be. Basically, like, we're thinking, hey, if I did that normal CDF, start, end, I need the mean and the standard deviation to find that probability. So I need to go find the mean and the standard deviation. I don't know those. So to find the mean, we can just add up all those means separately. Now to find the standard deviation, well, we would first do the variances. Oh, I don't know why I just wrote a mu there. But since all those are the same, it's like saying I'm going to have 4 of the standard deviations squared. All right, so that might be a little bit easier way to think about it. And then to find the standard deviation, I would have to take the square root of that. So here it is if you wanted to write it all out. It's kind of up to you. I like to make things easier. And we got 0.16. All right, so now I can fill in my mean and my standard deviation. And that would give you an answer of, I don't remember off the top of my head. All right, so 0.846955. Okay. However, just putting that normal CDF is not enough work. We've talked about this. You could make a density curve, or you could describe the density curve. So the area under the density curve from 8.5 to 9 with a mean of 0.0256 and a standard deviation of 0.16 is the 0.846955. So the area under the density curve with a mean of 0.0256 and standard deviation of 0.16 from 8.5 to 9 is 0.846955. Interpreting that, it tells us that there is about an 85% chance that Mr. Starnes' tea will taste just right. Well, hopefully it works for you, Mr. Starnes. Okay. All right. Suppose the height m of male speed daters follows a normal distribution with a mean of 70 inches and a standard deviation of 3.5 inches. And suppose the height f of female speed daters follows a normal distribution with a mean of 65 inches and a standard deviation of 3 inches. What is the probability that a randomly selected male speed dater is taller than the randomly selected female speed dater with whom he is paired? All right, so what is this asking us to find? The probability that the male is taller than the female. So there's a couple ways you could write that. You could say, what's the probability that the male minus the female is greater than 0? Or you could put, what's the probability that 0 is greater than female minus male? I don't care which way you do it. I'm going to do it the first way. So I need to find the mean, the standard deviation, and if I want it greater than 0, so basically we're thinking we want to get it into the normal CDF, 0 and greater, so greater than 0, with the mean and the standard deviation. So I need to find what those are for the event m minus f. All right, well, the mean's not too bad. You just subtract. So 70 for the male. So the mean of the male minus the mean of the female is 70 minus 65, which is 5. The standard deviation for m minus female is going to be that square root of the the males, which was 3.5 squared, plus, do you hear me on this? Plus the female's standard deviation squared. So even though our event was subtraction, standard deviation is always addition. And get those, let's see, that's about 4.60977. So now you can put those into your calculator for the normal CDF. And I got it to be 0.86095. So the area under the density curve with a mean of 5 and a standard deviation of 4.6 from 0 to infinity is approximately 0.86095. So this tells me the probability of a randomly selected male being taller is about 86%. Okay, and there's my little graph if you like to do a graph. I would always do the graph on the in your notes. I would always put this in there, and I'd also put it in on the AP test. I just think this will give you credit very, very easily. So there was the mean. I kind of said, you know, at the point of inflection, getting that standard deviation. So one away in each direction. And then I kind of showed I wanted it from 0 to infinity with all of that area filled in. Okay? So 6.2 in summary, adding a constant a, multiplying by a, linear transformations, all of that fun stuff. Adding and subtracting and all of those probabilities and interpreting and fun stuff. Sorry, back here. Adding and subtracting with what's going on. So like if you add, you always add both for the means and the standard deviations. If you subtract, you're going to add the means and, or sorry, subtract the means and add the standard deviations. But there you go. And we're going to be starting 6.3 next. I'll see you then.